Alright, my name is Kyle Lambert, and I'm the lead for Group 2. Today I'm going to be talking about next week's experiment. It's Experiment 7, which is the small engine dyno. Alright, so what we're going to do in the presentation is just talk about some goals we have, and then we're going to go over the thermodynamic background of just what we're going to do, talk about the apparatus we're going to use, and we're going to talk about safety, which can't really be stressed enough with this experiment because it says like 9 times in the manual this is the most dangerous one we do. So, our goals. We're going to show the variation of engine parameters under 2 distinct cases. The first one, we're going to have a constant engine speed, and we're going to adjust the load we apply to it, and we'll see how the horsepower and torque and other parameters change given this scenario. And then we're going to do a second case where we actually keep the load constant and then throttle the motor up and get the same readings, but they'll be a little different. So just our 2 cases. First one, constant speed, engine RPMs don't change. Second one, we do change RPMs. So, the background of this experiment. As you can see here, the whole point of a motor is to turn chemical energy into mechanical energy through combustion. So, the way this works, the engines we're using are all basically auto cycle motors. We'll talk a little more about that later. There's going to be 4 strokes generally. And what will happen, you have to turn an explosion, which drives a linear mass into rotational energy. So your first stroke is going to be the intake. You're going to pull the piston down in the cylinder. Air will come in, air and fuel. Next is compression. It all comes up, pushes it together, squeezes it tight, and then you have your boom, and you have the combustion or power stroke as the rapid expansion actually pushes the piston back down, and then the momentum as it swings around in the crank, it comes back up, the exhaust valve opens and it pushes all the exhaust out of your car. So, some things we need to know when we're talking about engine parameters, engine performance. We need to know how much air is going in, and we do approximate with, we don't account for the fuel not actually being a gas per se. So we approximate things with our airflow, and then volumetric efficiency is going to be another important factor that deals with how much power you got out the motor, how efficient everything is. We actually have a few different types of efficiency that we care about in motors. And as you can see here, the conversion of energy and the mechanical efficiency of the motor itself. Other than that, we have our base power equations, which is definitely deals with a lot of different efficiencies and things to get a net power output. So the motor we're going to be using is 1 cylinder. It's a reciprocating type of motor, so the piston's going up and down. It's not like a rotary like in some other cars where it just spins. And it's going to be a 4-stroke motor, not like a 2-stroke or a boat or bike, whatever. And what we need for the lab is a test stand, the throttle actuator, as you can see over here, which is actually just a brace to pull the throttle. Choke, which will restrict the amount of air that can go into the motor initially. The dynamometer itself, which we'll talk more on later. And then we have the torque arm and motor, which are also just going to go here, holding everything down. The motors, but actually we're measuring. Just a little blown up diagram. So, safety. Ears and eyes have to be on at all times. There's fumes, there's rotating things, chains can definitely mess you up, and stuff's going to get hot. So these are all definitely things to look out for. And worst comes to worst, the space bar is an automatic emergency stop, but don't push it unless somebody's losing an arm or something. If they are, just turn the key off. It's not that bad. So the procedure, it's very long. It would be 10 minutes and stuff to talk, so we'll skip over parts of it and do it in the lab. But we're going to reread the safety instructions, and then we'll check the wiring. There's an AFR gauge, which is the air fuel mixture gauge. Tells you how complete your combustion is. And we're going to check the wiring of that, check the load valve and the water lines, make sure they turn the exhaust fan on so it gets the exhaust and the carbon monoxide and dioxide out of the room. There are monitors in the room also from the safety talks. If they go off at any point, turn the motor off and leave. We'll set up the JRK screen. All this is actually going to be done on a computer. It sets up the experiment, sets it up to collect data and the motor to run. Then we'll turn the key on, which won't start it. Every time we start the motor, there's a key on the computer that we're going to hit. And once we've done that, we'll turn on, we'll let the thing warm up, and then we can start doing the pulls. And we'll repeat the test 4 times just so we get a good accurate data spread. and we'll save that data to the computer. So, some things we need to know about. This is our typical thermodynamics class approximated Otto cycle. Doesn't exist in the real world. You can't do anything perfectly efficient. What it ends up looking like is this over here. And most times if you cut this little chunk off down the bottom, it's a better approximation. But all of this down here and up top deals with the valve opening and the overlap of valves. There's points where they're both open at the same time. And that causes all sorts of crazy things that aren't very efficient. So how the water brake dyno works, the motor will turn a shaft, which actually will put pump water through it, and there's a resistance inherent in that. And then we will measure the output, the electrical output from the stator, and we'll convert it into power numbers. And here's just what your basic horsepower and torque curve should look like. So here we have torque up top, and horsepower comes over and crosses it. Should cross it at 5250. There's an equation to use when we talk about power and torque. It's horsepower equals torque times RPM over 5250, give or take. And that's one way to know if your dyno's reading accurately. If they don't cross right about there, then you can't really believe your numbers. You mess something up when you recheck. And that's it.
I have a question for you.
Yes.
So that's horsepower, torque, graph. So what's the third line?
Oh, this is actually the air-fuel mixture right here. You want to keep it usually between 12 and 14. 14 is a little lean. 13 is fine. So this just, as you run the motor, it will change with RPMs and the tuning of the motor. And that's why we see like a little lip over here. You want to keep it as constant as possible, but it's not always possible.